Now moving on to the regression part. Which model would be most appropriate, the most appropriate linear model for the following data set? So the first one is just something, like the first option is just something of the form y is equal to mx plus b, but that doesn't really seem like it would fit the plot we have. The second one seems like it's a polynomial, right? But with a little bit more digging, we see that the correct option is actually the third one. And this is something we actually saw in class. It's not the fourth option because that's not linear, right? Because we have one of the parameters inside, like our theta 3 is not linear compared to theta 1 and theta 2, right? Sure, y is a non-linear function of x, but a linear model means that it's just linear in terms of theta. It doesn't have to be linear in terms of x, right? And so you see if we fit theta 1x plus theta 2 sine x, and this is something we've seen in class before, it will roughly look like the figure that's given in 25. Okay. 26, which of the following depicts models with the largest bias? So we see the only one that works is the second option. And the reason for that is because the first option has very, very little bias, right? And bias, again, is just a measure of how off your prediction is, right? And we see here that the residuals are very, very low, right? So it's probably not the first one. And it's also the same case for the third one, right? The residuals are relatively low. Whereas for the middle one, we see that our the model in the middle is less complex than both the first option and the third option, right? And we know that when we have a less complex model, we'll probably have larger bias but lower variance. So this sort of matches our intuition. So the correct option is the second one. 27, given a full rank feature matrix phi and response values y, what does the following equation compute? And so we'll go over a derivation of it now, but what it actually computes is 0. Okay, and so why that's the case? Well, if we multiply in this phi transpose, we'll get phi transpose y minus phi transpose phi times phi transpose phi inverse phi transpose y. But we see when we multiply phi transpose phi by the inverse of phi transpose phi, that will cancel out, giving us just the identity matrix. So now we're left with phi transpose y minus phi transpose y, which is indeed 0. Okay? And the way you actually get this equation is by saying that phi is orthogonal. And I mean, this is not necessarily part of the question, but just for your additional knowledge, we know that phi has to be orthogonal to the error, which is y minus phi theta. And if you plug in the optimal value of theta from the normal equation and say that phi transpose times the error has to be 0, when you look at phi transpose y minus phi theta, you will see that it ends up being 0. Okay, and the equation that we're giving in the question is just one step simplified from what I just mentioned. Okay, 28, which of the following loss functions is most sensitive to extreme outliers? So the solutions are actually incorrect here. This is something we mentioned many times in class. It's the squared loss. The reason for that is because we're taking, the absolute difference between the predicted value and the true value and squaring that difference, right? So if we have some value that's completely off, we're going to take that delta and square it, right? Whereas, in absolute loss, we're not squaring any of these differences, okay? So that should be squared loss. 29, given a data set of 100 tweets where each tweet is no longer than 10 words, we apply a bag of words featurization to the tweets with the vocabulary of 10,000 unique words, plus an additional bias term. And our goal is to predict the number of retweets from the text of the tweet. Because the words are nominal, this is a classification task. That's not quite true. We want to predict the number of retweets. We're not predicting some sort of label, right? So this isn't a classification task. It's a regression task. Okay, so that's false. Okay, the feature slash covariance matrix, including the bias term, has 100 rows and how many columns, including the zero value columns. So we know that we have 10,000 features plus a bias term, right? So that means there's 10,000 columns, one for each of the unique words that we choose, and one extra for the bias column, right? And that bias term will always look like 1, 1, 1, right? Just for example, when we were doing two-dimensional linear regression, we wanted to fit something to y is equal to mx plus b. Our phi matrix would look like one column of all ones, and then an x1, x2, so on and so forth, right? And that's our bias column. So our number of features is 10,000 plus 1, which is 10,001. Okay, C, there's also some sort of typo in the question. It says because n is greater than d, the solution to the normal equations is not well defined. Okay, here n is actually less than d, right? Here n is 100 and d is 10,001, right? So this should actually read n is less than d, but the answer is still true. Okay, because let's look at what we have. We have that there's 100 rows but 10,001 columns, so our matrix will look like this. And we know that matrices that are wide or fat like this don't have full rank. Okay, so if phi doesn't have full rank, then phi transpose phi, which has the same rank as phi, will not be invertible. Okay, so the solution to the normal equations is not well defined in this case. Cool. D, by applying L1 regularization, we may be able to identify informative words. That's true. As we know, L1 regularization or lasso regression encourages sparsity in terms of the weights in our theta vector, and it sets many of them to 0. And so that essentially does some feature engineering for us, right? If it sets the weights of some features to 0, it'll tell us that those features may not be important when you're creating your model. Okay. In the process of training linear models with different numbers of features, you created the following plot, but forgot to include the y-axis label. Okay. Which of the following things could potentially be the y-axis? Okay. So let's see. We know for the bias, it must be false. Okay, because the more features you include, the bias will actually decrease. Okay, but we see here the bias decreases and then starts increasing again. But the more features we add, our model is becoming more and more complex, which increases the variance but decreases the bias. So this cannot possibly be the bias. And it also cannot possibly be the variance. Okay, because the more features we add, the variance is strictly increasing, right? And so for this, it's helpful to look back at the bias-variance trade-off diagram that's seen in lecture many times, where it shows bias going down, variance going up, and then test error looking something like this. Right, so that's test error. This one's variance. This one's bias. Right, we see that variance has to be strictly increasing, so that doesn't look right. Could it be test error? And so for this one, it's actually true because it sort of follows this diagram that we've seen before in lecture, right? Our test error will decrease until we get to some optimal number of features and then start increasing again. Okay? And could it possibly be the training error? That's also false. Because as we make our model more and more complex on the training error, the training error will strictly decrease. Okay, there's no reason for the training error to start increasing again if we're making our model more and more complex. Okay, the testing error will testing error will start increasing if we make our model more and more complex, because we're not training our model on the testing data, right? We're only training it on the training set. Okay, so the only one of these situations which is potentially true is C, the test error. Okay, and again, it's probably helpful to go and look at that bias variance test error diagram that we've seen many times in lecture. Cool. Okay, now in question 31, we're told to consider this model training script to estimate the training error. And in part A, we're told that line 5, right here, has a serious mistake, and are assuming our eventual goal is to compute the training error. Which of the following fixes that mistake? Okay, so the mistake itself is that you never fit your model using the testing data, right? The whole point of the testing data is that it's unseen throughout the model training and validation process, and you only test with it at the very end once your model is already trained, okay? So that's the mistake, and we always fit with X train and Y train. So that would fix that mistake. In B, we're told line 10 contains a serious mistake, and assuming we've already corrected the mistake in line 5, which of the following fixes the mistake on line 10? Okay, so we want to find, again, the training error, right? So we want to find the RMSE between the true Y values and the predicted Y values, okay? And we see here, Y fitted are the predicted values for our training set. So our predicted is Y fitted. Right? This question is intentionally misleading because there's also a Y underscore predicted, but that's when we predict using the test set, which we're not dealing with at all in this question, right? We're trying to find the training error. So for our cases, the predicted values are Y fitted, and the true values are just Y trained, because that's sort of what's given in our data set. So we want whichever one gives us the RMSE of Y fitted and Y trained, which happens to be the last option. Okay, and now 32, which of the following techniques could be used to reduce overfitting? Well, let's see. So we know that overfitting is usually a consequence of having our model being too complex, so having too many features. So what we probably want to do is reduce features, right? Reduce features so our model doesn't overfit to whatever we're training it on, okay? So it can't be the last option because that's the opposite of what we want. We want to remove features, not add. It can't be the second last option because we never fit our model to the training data, or to the test data, right? We never fit to the test data. And the first one also doesn't really make sense. We would never make our data worse than it already is, right? So we would never add noise to our data. So the correct option is the second one. We use cross-validation to remove features because, again, the more features we have, the more we run the risk of overfitting, so we probably want to reduce features. Okay. Now in 33, suppose we're given a data set where xi is some scalar real number and yi is the real valued response. To model this data, you choose a model characterized by the following loss function. Okay, and so now we need to determine whether or not this model includes a bias/intercept term. And it turns out that it does, so that's true. And the reason for that is because you know the loss function is probably going to look like y minus y predicted, right? And so here, yi is the true y value, and the predicted y value seems like it's this quantity. So it seems like our model is y is equal to theta naught plus xi cubed theta 1. Okay? So it looks like that's our model. And it does include a bias/intercept term. It's the theta naught. If it didn't, it would just look like yi minus xi cubed times theta 1. But there is a bias/intercept term, right? It's that y is equal to mx plus b part. Okay? As lambda decreases to smaller values, the model will reduce to a constant theta naught. That's false, right? As lambda decreases, we're essentially just removing the regularization, okay? This would be true if lambda increased, right? Because if lambda increases, we're forcing our model to be less and less complex. But as lambda decreases, we're not restricting our model in any way. But this is implying that by decreasing lambda, we're restricting our model, which is not the case. So this is false. C, larger lambda values help reduce the chances of overfitting. That's true because larger lambda values force our model to be less and less complex, giving us lowering the probability of overfitting, because our features are just less complex. Okay, they can't fit to that much data. D, increasing lambda decreases model variance. That's true, because again, increasing lambda decreases model complexity, right? Remember, lambda is inversely to model complexity, and model complexity and variance are proportional to one another, right? So if we increase lambda, we're making sure our model is less and less complex, so we're decreasing the variance, though we are increasing the bias. And E, training errors should be used to determine the best value for lambda. And so this is a subtle one, but this is false, right? To determine the best value for lambda, we probably want to do cross-validation, and in that case, we want to use the validation error, right? Because when we're doing cross-validation, we and if we're doing k-fold cross-validation, we'll use our validation data and the validation error. Okay, so that wraps up this portion of the exam.